This is a Stellarium video on precession, the precession of the equinoxes, and the effects of precession that you can see in the sky if you observe for a long enough period of time, because the precession cycle is very slow. It takes about 26,000 years for it to go through one cycle. So the Earth spins on its axis once per day, so the Earth has a rotational axis that actually defines the Earth's equator and the celestial equator and the North and South Pole, the North and South celestial pole. As the Earth spins on its axis, it acts like a gyroscope or acts like a top. Now, the axis is not in line with the axis of orbit around the Sun. So if we watch this video here, you can see that the Earth is rotating to the east, so counterclockwise as seen from above. And that axis is tilted relative to its orbital plane, which is kind of horizontal in this video, in this animation. You can actually see the axis of the orbit of the Earth around the Sun is going to be along this terminator line between night and day, because the Sun has to be off exactly to the left in order to illuminate that side of the Earth, like so. So the axis of rotation of the Earth is tilted by 23.5 degrees. And of course, that's what causes the seasons and the variations in declination of the Sun, from the summer solstice at plus 23.5 degrees down to the winter solstice at negative 23.5 degrees. So why does the Earth precess around like this? The two periods here are not to scale. It actually, since it takes 26,000 years for the axis to precess all the way around like so, it would actually be many, many, many days. Of course, 26,000 times 365 days, that many rotations for the axis to go all the way around. So the Earth acts like a gyroscope, and if you have a spinning gyroscope and you grab it and try to twist it, give it a torque, it will not move the direction you turn it. It will actually move perpendicular to that direction. And of course, that's how a bicycle wheel can actually balance when you try and tip it over. In this case, the Earth is not a perfect sphere because it is rotating. It actually bulges at the equator, and the Sun and the Moon tug on the equatorial bulge, making the Earth try to torque so that the axis of rotation lines up with the axis of the orbit. But as a gyroscope, the Earth doesn't turn that way. It just precesses around kind of a big cone-shaped circle. The poles make this cone-shaped circle around once per 26,000 years. So what are the effects that you can observe? Well, one of them is that the direction that the North Pole is pointing, or the direction that the South Pole is pointing, is going to move around in a big circle with an angular radius of 23.5 degrees. Right now, the North Celestial Pole points at the star Polaris, so we have a North Star, and as the Earth spins on its axis, that star stays fixed in the local sky. But due to precession, the axis shifts away from those stars. Maybe over here it's pointing at Polaris, and then 13,000 years later it's pointed over here at some other patch of sky. There may or may not be a star there. And so that affects whether or not there's a pole star, and which star is the pole star. Let's take a look at that in Stellarium. So here we are in New Haven. It's February 2016. I want to look to the north so we can find the North Star. And we'll go to, speed up time here so we can get to sunset. All right. And that, of course, is Polaris right there. There's a nice trick using the Big Dipper to help you find Polaris. This is the handle of the Big Dipper. This is the cup. The two stars at the end of the cup will point at Polaris, so that helps you find the North Star. If I turn on the equatorial grid, the lines of right ascension and declination, you can actually see exactly where the North Celestial Pole is, where all of those lines come together. So actually I can zoom in a little bit on that so you can see Polaris is not exactly right on the North Celestial Pole. It's about 41 arc minutes off of the North Celestial Pole this year. Now astronomers know about this, and you can actually correct for that if you know what time of night it is and what season of the year it is. You know that, oh, Polaris is a little bit to the left or a little bit below the actual North Celestial Pole, and you can adjust for that if you need to find true north to align a telescope or for whatever purpose. So as the evening progresses, you can see the whole sky appears to spin around the North Celestial Pole, and Polaris is fairly close to that. Famously, Julius Caesar says in the Shakespeare play, "I am as constant as the northern star." And actually, if we were to go back in time, let's stop time here, and let's go back to the time of Shakespeare. So let's go back to around 1600 or so. Polaris was less constant then than it is now. Now there's about a 2 or 3 degree difference between Polaris and the North Celestial Pole. So if we watch the sky rotate now, you can see that Polaris is making a bigger circle around the North Celestial Pole. There are certain seasons of the year when you wouldn't be able to see Polaris above or below there, like right there. Just in February, the sun is up when Polaris is above the North Celestial Pole. I'm not too concerned about that. I'm going to turn off atmosphere so that we don't lose it during the daytime. Now, if we were to actually go back to the time of Julius Caesar, stop that, then the North Celestial Pole is even further away from Polaris. If we go back to, let's say, 46 BC, it's a bad year for Caesar. Right. Now, if we let time pass again, and I'll mark Polaris again, you can see, oh, it's a good, I'd say, 15 degrees or so away from the North Celestial Pole. So Julius Caesar would not have actually used Polaris as the North Star. You could actually perhaps use the Little Dipper to find the North Celestial Pole. This is the handle of the Little Dipper here. Let's stop that, and I can turn on the constellation lines for you. This is the handle of the Little Dipper, and then here's the cup of the Little Dipper. And these two stars at the end of the cup actually point to the North Celestial Pole, even though there's really no star there. If we go back even further in time, that you can find other stars. For example, if we go back to about 3000 or so BC, you can see the star Thuban right there in the constellation of Draco is fairly close to the North Celestial Pole. Now, it's not as bright as Polaris, but you can certainly see it with the naked eye, of course, especially before the days of light pollution. If we go back even further, let's go back maybe 13,000 years. The star Vega, a very bright star in Lyra, is closer to the North Celestial Pole than other bright stars. So maybe if you knew a correction, you could use that to find north. But our caveman ancestors perhaps used Vega to figure out which way is north. Well, there's no evidence of that, but maybe that happened. If we go back 26,000 years from 2016, then we'll have made one full precession cycle, and Polaris should be back close to the North Celestial Pole. So let's go back to roughly 24,000 BC. And I'm not getting it exactly right, but there you see Polaris is back close to the North Celestial Pole, and we've gone through one full cycle. Another effect that you get with precession is that the position of the equinoxes will change. So the intersection, the line of intersection between the equatorial plane, there you see on the globe of the Earth, and the ecliptic plane, which is more or less horizontal in this animation, the point where they intersect is going to make a big circle in both planes all the way around once per 26,000 years. So where the equinox points on the celestial sphere is going to move around. So let's actually take a look at that as well. I'm going to reset back to 2016, and we're going to try and find the equinox. Let's look around here to the south. Leave the atmosphere off for now. So let's turn on the celestial equator so we can see when the sun's going to be on the celestial equator. So there's the equator. Let's also turn on the ecliptic line, which shows us the path of the sun around the celestial sphere. So here in February 24th, the sun is a little bit to the west of the point where it crosses the equator. So we should actually see the sun on the equator at declination 0 at some point. Oh, got the really wrong year here. Let's put that back. All right. The Gregorian year isn't perfect if you go 10,000 years into the future. But for now, the Gregorian year is designed to stay in sync with the tropical year and keep the spring equinox close to March 20th. And it might be a little bit before, a little bit after, depending on where you are in the leap year cycle. But there it is right there. So that point right there is where it is, just because the pole is pointing off that way. Remember, it's going to be 90 degrees relative to the equator when you turn the the grid back on so you can see the declination and the right ascension lines. And so as the pole precesses around, this point is also going to precess around. Let me go a couple of months ahead to get the sun just off of that point. And then I want to look at that point and just keep track of it relative to the stars. Now it's below the ground there at that time. I'm just going to hide the ground. So I'll use the hide the ground option. Please forget where it is. It's the trees. There we go. And I want to orient myself so that the equator stays horizontal. So there's equatorial mount mode. All right. And let's see. So here we are now. Actually, there's the spring equinox right there. So let's zoom in on that a little bit. All right. And by definition, we define celestial longitude, the right ascension circles, as being 0 at that point on the celestial sphere. So there you see 0 hours, same as 0 degrees, but right ascension is in hours. Now let's see what happens year after year. So keep an eye on that point, and if we let time pass, every so often the moon comes through and there we go. Every so often the moon comes through and changes the contrast on the sky there. So see how that point is moving relative to the stars. So these stars that are fairly close to the 0 right ascension circle should have right ascension coordinates. Let's see, let's pick that one right there. Right ascension coordinates very close to 0. They're 29 hours, 59 minutes, 44 seconds. And as each year passes, you see it drifts off to the east, sort of parallel to the ecliptic, because the precession is carrying this point around to the west as the Earth's axis precesses. Now, this is the reason why right ascension and declination coordinates always have a year associated with them. So here you see it says right ascension declination of date. And so those are the coordinates for 2080. But then also up here it says right ascension declination for the year 2000. So this is how astronomers deal with the changing equinox position. We tabulate the coordinates for stars or galaxies or whatever you're trying to keep track of every 50 years and put those coordinates in a catalog. So we used to use the coordinates for 1950. These days we use the coordinates for 2000. And at some point we'll switch over to using the coordinates for 2050. But it's very important that you know exactly what coordinate system your telescope or your computer is using when you try to go find these objects in the sky, because you could point at the wrong patch of sky just because you're not taking the precession of the equinox into account. Now, in terms of other things you can observe, what this means is that where the sun is relative to the stars on particular points in the seasonal year, the spring equinox, the summer solstice, the fall equinox, and so forth, it's going to be in front of different stars as the precession cycle happens. This is why people's sun signs don't really line up the way they're supposed to anymore. For example, I was born in August. Go to my birthday here, and my sun sign is supposedly a Leo, and so if I were to go find, okay, where is the sun today? There's the sun over there, and it looks like the sun is actually in the constellation of Cancer, although it's not too far away from Leo. It's kind of midway between Cancer and Leo, because I think I'm near the end of the time range for Leo. Well, that's because the starting point when astrology was established thousands of years ago was in Aries. So the spring equinox happened in Aries. So if we look actually at where the spring equinox is today, what constellation is it in? It's sort of in Pisces, although it's kind of halfway between Pisces and Aquarius. But if we go back 1,000 years, you can see there it's more solidly in Pisces. If we go back 2,000 years, you can see, yeah, it's still pretty much in Pisces. If we go back 3,000 years, negative 1,000, you can see now here it is in the constellation of Aries. Aries is a very dim constellation, but it gets its own 30 degrees of the ecliptic kind of right around here. If we go back 5,000 years, well, to 5,000 BC, so 7,000 years, you can see here it is over here in Gemini. So in the spring, the sun would have been in Gemini, and the constellations you'd see, for example, rising opposite the sun would shift every 2,000 years. They'd shift up by one zodiac sign. Another example of this is that it's a useful rule of thumb to know that when the sun sets on the winter solstice, let's go back to 2016, when the sun sets on the winter solstice, the constellation of Orion is rising in the west. So let's go to the winter solstice, December 21st, more or less. And we'll go back to the horizon mode because I want to see the sun setting. Turn on the ground. We'll go back to orient to the horizon. And then I want to try and find sunsets. All right, there's the sun up in the sky. Turn the atmosphere back on, and let's go to sunset. All right. So as the sun sets in the west on the day of the winter solstice, you have the constellation of Orion rising in the east. So what stars are behind the sun or opposite the sun, 90 degrees to the sun, will shift with precession in terms of the seasonal year. So if we go back 1,000 years, Orion was higher in the sky at sunset. If we go back 2,000 years, it's even higher at sunset. If we go back a good chunk of time, let's even go back that 7,000 years I did before, there you see Orion is quite far from the celestial equator. It's kind of creeped down to the south because of the way that the equinoxes have precessed around. And so it's no longer a good marker for the winter solstice. This is the peril of using a sidereal cycle, where is the sun relative to the stars, to track a tropical cycle or a seasonal cycle. Because of precession, they'll very slowly get out of sync. So for example, let's say you had a temple or an architectural alignment that you thought aligned with a particular star because it aligns with a particular azimuth, maybe where the bright star Sirius rises or the bright star Canopus. That will actually shift. The direction where that star rises on the horizon will shift over a 26,000 year cycle. Now you can actually use that potentially to date observations. If you have evidence that a star was supposed to rise at a particular altitude, or particular azimuth, you could actually use precession to help you date when would that have happened at a particular latitude. Now it's an interesting question to see if precession would affect the solstice alignments. So we've talked about Stonehenge and how the main axis of Stonehenge appears to align with the direction of the summer solstice sunrise. And then in 180 degrees in the other direction, it aligns with the winter solstice sunset. Now Stonehenge is very old. The layout of the stones maybe go back to 2,500 or so BC. But the alignment with the solstice is probably much, much older, perhaps going back 5, 6, 7,000 BC or so. So would that alignment break due to precession? Well, it's important to remember that the solstice directions are determined by the extremes of declination of the sun from minus 23.5 to plus 23.5 and the latitude of your site. So if the latitude of Stonehenge doesn't change, would the extremes of declination of the sun change? So when the sun is shining more directly on the southern hemisphere, that's going to be our winter solstice, and also for Stonehenge. When the sun's shining more directly on the northern hemisphere, that'll be our summer solstice. The only reason those declinations, plus or minus 23.5, would change would be if the degree of tilt changed. If the Earth had less tilt or if the Earth had more tilt. If the Earth had less tilt, we'd have less extreme seasons and the variation of declination of the sun would be less. If we had more tilt, we'd have more extreme seasons and the sun might go plus or minus 30 degrees or 45 degrees or 60 degrees if we had a bigger tilt. The Earth's tilt, the degree of tilt, the obliquity, does change very slowly. That's an effect called nutation over a much longer time span, roughly 100,000 years instead of 26,000 years. So that should not affect the solstice alignments. And let's just check that in Stellarium quickly. So let's go back to 2016. And let's go to see where the sun rises on the summer solstice. So here we are. And so let's go look in the east and find a sunrise. I don't have a Stonehenge circle set up in the horizon. It would actually be possible in Stellarium to upload a custom horizon that would have the stones as you see them from the center of the circle. What do I have? What might serve as a front sight here for my solar observatory? Well, if I let the sun cross the horizon here, you can see, yeah, there's kind of a notch in the horizon image background. I could use that as a marker to see if the sun's going to rise at that point. It's important to check and make sure that that really is an extreme northern declination of the sun. I can just check that here and see, oh yeah, it's 23 degrees, 26 minutes. I could also, step forward a couple days or backwards a couple days and make sure that the sun really is at an extreme there. If we go back 1,000 years and look and see, okay, well, where's the sun going to rise? Rising at pretty much the same azimuth. We go back 2,000 years. Again, sun's rising at the same azimuth on the solstice. If we go back to the time of Stonehenge, let's go back to 2500 BC. All right. Now it looks like it's at a different azimuth. It looks like it's rising at a different azimuth. So maybe it's broken. Well, this is the Gregorian calendar, and the Gregorian calendar does actually lose days relative to the tropical cycle. So I'm going to actually kind of fish around and make sure that I'm at an extreme point of declination. That looks pretty good right about there. You can see the sun was in Leo, in the direction of Leo in 2500 BC. So instead of having the Tropic of Cancer, we'd have the Tropic of Leo. All right, now where is the sun rising at? What azimuth? Oh, that same azimuth, right? Because the extremes of declination of the sun haven't changed very much. Maybe it's changed by a fraction of a degree due to nutation, but not enough to affect the precision of these alignments. So solstice alignments seem to be fairly robust over thousands of years, but directions to where stars rise will change significantly over a few thousand years because of the precession effect.